Consider uh, n-dimensional autonomous, real autonomous system of uh, this form. Okay. In such cases, when x is equal to a, f of a is a vector with its tail point at a. Okay. Basically, the vector starts at a tail point at x equal to a. Sorry, tail point at a. Okay. So if this is point A, and where is this point A set up? So let's say that this is an n-dimensional autonomous system, as I said. So for each variable you set up axis. So for x1 you set up axis, for x2 you set up axis, and do so till you set up axis for xn. So now you have an axis system with you. Okay. Let's say that n is equal to 2. For n equal to let's say that for n equal to 2 you have x to be equal to x1 and x2. Okay, so this is a vector that you have x1 x2. So let's say you set up a axis which is axis system which is of this form. So this represents how x1, this axis is how x1 evolves, this axis is for x2. Now a is a point somewhere here. Okay, we'll call this point as a in this particular state space. The access system that you set up is the state space that you have set up for the system. Okay. Now at A, f of A is essentially a vector. So it a vector starting at A. So what does it say? If you are at A, then what is the direction in which you are going to evolve and with what magnitude? Okay, so if you assume that this autonomous system that you have in hand has a solution and the solution is unique, then x of t is going to be the solution. At every instant of time you will have a value associated with the vector x. Okay, you keep on plotting the points that you get for each instant of time on the state space that you have constructed. Okay, for example, in this particular um, two-dimensional system, let's say that you started somewhere at A, so the next point that you get at some instant of time would be here, next instant is here, and this is how you keep on getting your points. So essentially what x of t represents is, if you remove the t part and you have the collection of the points through which this trajectory, through which this line that you see or the solution that you see is going to pass, then essentially you are getting a locus of you're getting a locus on the state space. Okay, so this is the locus that you are actually going to get, and this is what the solution is going to be. Okay, so if you observe from here, the vector f at every, the vector f of x at a given point x on the solution trajectory is always going to be tangential, okay, to the solution trajectory, and this is the locus that we have. So this locus that you get on the state space is known as the trajectory. It's basically a plot between x1 versus x2 versus x3 versus x4 that you it's a plot that you get. And how do you get those points? Those points are nothing but the solution to the differential equation. So that is the locus, and we call that locus as the trajectory, or also known as the orbit. Okay, the axis system that we set up is known as the state space. In case of a two-dimensional system, we can call it as a state plane as well. It is also known as phase space or phase plane. Okay, the axis system that you set up is known as the state space or phase space. Okay, for a two-dimensional system, You can call it as a state plane or a phase plane. And when the solution trajectory is plotted on the state space, then solution is plotted on the state space, we call it as a trajectory or the orbit of a system. And in this case, because we are showing this trajectory to start at A, so the initial condition is essentially said to be A. Okay. Now, if you set up a state space, okay, if you have that state space with you, at every point in the state space, you have a trajectory, you have a vector associated with it. Okay. So in a state space, at every point, let's say x, there is a vector associated. There is a vector f of x associated with x. Okay, so the vector f of x essentially starts at x, right? So if we want to basically identify this vector, we identify this vector with its starting point and f of x. Okay, so the collection of all these vectors, okay, so let's say that um, this calligraphy x is a collection of all the vectors represented with the starting point and the direction and magnitude, with of course, because we are considering real vectors, and f being a map from Rn to Rn, we call this set as the vector field. Okay, so the vector field here is set up on the state space that you have. Okay, um, now this, once you set up this vector field, so once you have vectors associated at every point on the state space, this gives you a qualitative idea about how the solution is going to look like given an initial condition. Okay, solution for an initial condition, it will give you a qualitative idea. It will also tell you whether there are equilibrium points or not for the system under consideration. Okay, note that all systems may not have equilibrium points. For example, consider the scalar system where x dot is equal to 1. Okay, it will not have any equilibrium points. Now, whether there are equilibrium points or not, and it will also tell you the behavior of the system in the neighborhood of the equilibrium points. So if you have initial, so we know that at equilibrium points x dot is 0, which means there is a 0 vector associated with every equilibrium point that you have on the state space. Okay, now if you start at a point which is arbitrarily close to the equilibrium point, but it is not the equilibrium point. Okay, you start somewhere which is not the equilibrium point, then there is a vector associated with it, a non-zero vector that is associated with it. Okay, and that vector, as we said, will indicate the direction of evolution and also the magnitude of evolution. And from there on, you will be able to predict the locus of the trajectory on the state space for the initial condition that you have chosen, right? So because you have this, it will give you an idea of that if you start at a point close to the equilibrium point, will the solution trajectory that will evolve have a tendency to go towards the equilibrium point, or will have a tendency to move away from the equilibrium point. Okay, so if you have initial condition close to an equilibrium point, from the vector field you can see whether trajectory have a tendency to move toward the equilibrium point under consideration, or trajectories have a tendency to move away from the equilibrium point that is under consideration. Okay, so in the former case, if they have a tendency to move toward the equilibrium point, we call them stable equilibrium points. If they have a tendency to move away from the equilibrium point, then we call them to be unstable equilibrium point. Okay, in some cases what you will also see that uh, the trajectories are essentially going to be closed orbits, so they are going to be closed paths, and the system just keeps on evolving on those paths. And if you remember, in our initial lectures we named them limit cycles. So you can have a estimate of where the limit cycles are going to be in the state space given the vector field without even solving for the system. Okay, so I'll show you some examples of how a vector field typically looks like, and how can you get see what the solution is going to look like. So for this, the first example that we'll take is a two-dimensional system where x1 dot is x2 and x2 dot so is minus 10 sine of x1 is the first system that we'll take. So for this, just give me a minute now because it is connecting to the MathWorks. Okay, so I think we are connected. Yeah. Okay. So for the system that we had, which was x1 dot equal to x2 and x2 dot to be equal to minus 10 sine x1, the vector field that you see are actually plotted with the blue arrows. So at every point there is a vector associated with it. Okay, now if you see the vectors, if you observe the vectors, then what you see is if you start at a point, then you are essentially going to follow a closed orbit and you will reach that point. Okay, to confirm this, we took a solution which is starting at the point 10. Okay, on this particular axis, and if you solve the differential equation, what you get is this black trajectory on this particular state plane, or the phase plane as you want to call. The horizontal axis represents the x1, the vertical axis here represents the x2. Okay, so the solution evolves. So you start at 10, then you actually keep on moving down, and you move away from x1 equal to 1 and go closer towards x2 axis, and this is where and then you reach x2 axis, and then again you reach x1 axis, then the x2 axis, and then x1 axis, and so on. So you keep on moving on, your solution keeps on evolving on this particular black trajectory. Okay, so what you see here is the existence of a limit cycle. Okay, you are on a limit cycle when or rather you are on a closed orbit. Okay, where you are actually moving on this particular path. Now similarly, if you take another example for a system x1 dot equal to minus to x1 and x2 dot to be equal to minus x2. So in this case, how the trajectory look like? So we started at the point 1 1. Again, the horizontal axis representing x1 and vertical axis representing x2. So we start at the point 1 1, and if you notice the trajectories, you are actually moving towards the origin. Okay, so the origin is the 0 0 point here, and the vector associated at origin is 0. So from here you can conclude that origin is essentially a equilibrium point. And if you can see, the trajectories are actually anywhere the trajectory starts in this state plane, they are helping in reducing the, not, I should not say reducing, um, well, they indicate that wherever you start, the trajectory is finally going to approach 0 0. Okay, so the black one is the trajectory shown for initial condition 1 1, and this is how it is actually going to evolve. And if you can see, it is going towards 0. Okay, but for all the systems that we see, for the system that we see here, it will actually reach the 0 as t approaches infinity. So it is now arbitrarily close to 0, but may not be, but is not on 0 as of now. Okay, so this is how it is going to evolve. So this black path that you see in this particular state plane is the trajectory, and we have what the blue arrows that we have set up represents the vector field. Okay, so similarly in this particular case also, the black path that you see is the trajectory. It's the locus that we get as the solution evolves with respect to initial condition. That's the trajectory that we have in the x1 x2 plane, and the vectors that we have set up represent the vector field. Okay, so I have only taken points between -2 to +2, and hence this is what the vector we get. If you want for -4 to +4, you can actually generate them. Okay, now again coming back to um, this particular system, x1 dot equal to x2 and x2 dot equal to -10 sin x1. If you look, we started for initial condition 1 0, and we saw that it is actually repeating. It is actually moving on a closed orbit. And similarly, for any initial condition you take, what you will observe is you will get a locus. Okay, or you will get a trajectory starting at that initial condition. So if you take the family of such curves, okay, so in this case the family of curves would be orbits all around in the plane. Okay, closed orbits. So if you take the family of all those curves that can be generated for any initial condition that you take on the state plane, then we call this family as the phase portrait. Okay, in some cases these trajectories are also known as the state space trajectory or the phase trajectory. And the family of all the trajectories family of all possible trajectories that you can think of for a given system n-dimensional real system that we are talking of. Okay, family of all trajectories, when I say trajectory, they are essentially solution curves. Okay, so family of all these trajectories is called as the phase portrait. Okay, now the problem with I would not say the problem, but we have a limitation with respect to this state plane trajectories that we plot on the state plane, and that is, once we plot the trajectory on the state plane, we lose the information of how the trajectory or how x1 and x2 have evolved with respect to time. Okay, so if I give you a trajectory, you will not be able to tell what the solution is going to be. So when I say solution, you essentially come to associate the time as well. So as at a particular t, what is the value of x? That is what the solution is. So the solutions are essentially, if you go back, the solution is x of t. This is the solution. So this is what we call as the solution curve. Okay. So if I give you a trajectory on the state space, then you'll not be able to recover the solution from this state space. So you exactly cannot tell what the solution is going to look like. What you can basically say is the solution will evolve such that the trajectory is going to look like this. So you cannot have a quantitative description of the solution, rather you have a qualitative description of the solution. So from you can be predict the qualitative behavior of the system as to whether the solution trajectory is going to diverge or not. Is the system's equilibrium point stable? Is the system's equilibrium point unstable, and so on? But you cannot exactly pinpoint which point the system will be at which point at which instant of time. So basically you lose the information about the solution that you have in hand. Okay, so this doesn't mean that state space trajectories or the phase portraits are essentially useless. No, they give you a lot of information. As I said, from the vector field, you come to know how the solutions are going to look like, whether there are equilibrium points or not. From the solution trajectories, you will essentially come to know whether the solution is remaining bounded or not. Is the solution becoming unbounded? Is the system undergoing oscillations? Okay, will the solutions go towards the equilibrium point or not? Will the solutions move away from the equilibrium point or not? And so on. Okay, so these are very important informations that you can actually get. You can also see whether the system is going to undergo oscillations which are decaying as time progresses and hence are actually going towards the equilibrium point, or which is possibly origin in this particular case. Okay, and so on. So these qualitative behaviors are very important and are essentially giving a very useful insight into the system that we are actually considering. So in the forthcoming lecture, in the next lecture, we'll see or we'll try to analyze certain qualitative behaviors, especially about the equilibrium points and possibly about how the system's trajectory might evolve with respect to one-dimensional systems and two-dimensional systems. Okay, why? Because it is easier to basically visualize them with respect to plots or with respect to diagrams as opposed to higher dimensional systems. So this will give us an idea of what we are actually, what kind of behaviors can be seen from the trajectories for a given system, and what kind of behaviors can one see from the vector fields for a given system, and then those ideas can be actually extended over to higher dimensional systems. Okay, so we'll stop here. Thank you.